Assalamualaikum, good days. So today I will be showing on how to use and interpret the pulse oximeter. So this is the pulse oximeter. So this part reflects this is the screen where it reflects the patient's oxygen saturations, heart rate, and also the battery level of this device. And at the back, this for the batteries. So you can insert batteries here, and this part okay, where you put on the patient fingers. Okay, so uh, first you turn on this device. Okay, and place it on the patient's fingers, and you just wait for maybe a couple of seconds for it to rate. Okay, okay. So this part reflects the oxygen saturations in the body, which is normal, 98%. So it should be more than 94. On the other side is the patient heartbeat. So the normal should be 60 to 100, unless if it is a baby or infant. So it could reach as high as 160 beats per minute. So in the middle is the battery level of the equipment. That's it. Okay, you can remove it and turn it off, or it will be auto off. So now we can I will show you the engineering behind this device, pulse oximeter. So let me share shortly the slide that I already prepared here. The pulse oximeter, which an instrument very critical to modern healthcare, that it is often regarded as fifth vital sign alongside temperature, pulse, respiratory rates, and blood pressure. So it was first introduced in 1980s. This non-invasive device monitors arterial oxygen saturation (SpO2) and heart rate. Its key capability lies in providing real-time, continuous data without the need for arterial blood sampling. So this versatility allows it to be used everywhere, from emergency medicines and anesthesia to home health monitoring. This is an infographic roadmap of the presentation, showing the path from engineering principles to limitation and design modifications. So we will explore the engineering principle behind this device, specifically how dual wavelength light absorption and Beer-Lambert's law allows us to see inside the body without breaking the skin. Then we address the critical accuracy barriers facing current technology, such as motion artifacts, low perfusion, and skin pigmentation issues. Finally, there will be a proposed next generation design architecture intend to resolve this limitation through enhanced signal processing and smart connectivity. Let's begin with the working mechanism. So the pulse oximeter operates by transmitting light through a vascular bed such as a finger. So it utilizes two specific LEDs chosen for cost efficiency and absorption characteristic, which is a red light at 660 nanometers and infrared light at 940 nanometers. So the physics here is deoxygenated hemoglobin absorbs more red light, while oxygenated hemoglobin absorbs more infrared light. So a photo detector on the opposite side capture the ratio of light that pass through, which allows the device to calculate oxygen level. The math behind the measure. So to turn the light signal into a number, device relies on a PPG signal. The signal received has two components: the DC components, which represents static tissue like bone and venous blood, and the AC components, which represents the uh, pulsatile arterial blood. So the microprocessor use common mode rejection to filter out the DC noise and isolate the arterial signal. So by using Beer-Lambert's law, which relates light absorbance to concentration and path length, so the device calculate the R value. So this is the ratio of red light absorbance to infrared light absorbance. The ratio is then converted into a SpO2 percentage, typically accurate within plus minus 2%, and a pulse rate derived from the frequency of the PPG peaks. The pulse oximeters has significant limitations that can lead to occult hypoxemia, the event where the device shows a normal reading despite low actual oxygen levels. So for example, here is limitation is motion artifact, where the patient's movement creates noise that mimics the arterial pulse, leading to false readings. The second is low perfusions. In patients with hypotension or hypoxemia, the pulsatile signal becomes too weak to distinguish from background noise. Then for carbon monoxide, the device cannot distinguish between oxygen and carbon monoxide. In poisoning cases, it may falsely show 100% saturation while the patient is suffocating. And then demographics. Finally, many devices were calibrated on healthy Caucasian volunteers. So high melanin levels in darker skin can scatter light differently, causing overestimations of oxygen saturations. These limitations bring us to the need for design modification. The current standard is the finger clip architecture, which is susceptible to motions and inaccurate in low perfusion states. So the proposed design focus on a few key areas. For example, for measurements principle, we want to increase sensitivity. And for the user experience, maybe we want to use the digital reading improvement, like the advanced sensor sensitivity and smart connectivity by using the wireless monitoring. So this final slide summarizes the proposed technical specification for this new design. So here we have the high sensitivity sensors to address low perfusion. We propose sensor capable of verifying accuracy even at 0.3% signal modulations. And then the motion tolerance algorithm. Uh, so we will implement specific frequency testing to filter out motion artifacts during physical activities, and also the smart interface. The device will feature variables pitch audio that strictly follows changes in SpO2, providing immediate auditory feedbacks to clinicians. So I think this we conclude my presentation today. Thank you for your time. Bye bye.